Hello guys, this is a video solution for the problem sheet for week 4. There are 8 questions. I will go through every single one of them and give you a detailed solution. Please note that this video solutions is on top of the typed solutions and the handwritten solutions which you can find on the course website. So the CDF So I'm going to use the following notation to denote the CDF, and this you can write like by definition is the probability capital X is less than or equal to X, and this is the probability that the maximum of X1 to X alpha less than or equal to little x. Now, if the max is less than or equal to a fixed number, then each of the random variables has to be less than or equal to x. Okay. Now, we are assuming that x1 to x alpha are independent random variables. So using independence, so I'm using, at this step here, I'm using independence of x1 to x alpha. Okay, let me put that in highlight. Okay. Now, in the next step, we are told that x1 to x alpha, each of them is an exponential random variable with parameter lambda. So this guy is, I'm sure you guys know the CDF of an exponential variable. So this is the CDF of this guy here, and so on, and the same thing for this. All right, so you've got the same thing repeated alpha times. So the final answer is this. All right, so this is the CDF of the most expensive asset. Part 2 of the sheet number 7 is to find the PDF. All right, I'm sure all of you know to find the PDF you simply differentiate. You differentiate the CDF with respect to x. So if you differentiate this with respect to x, this is what you will get. Right, so this is part 2. Part 3 is to find the nth moment of x. So let me go to a fresh page before I do that. All right, so here we have part 3. So we want to find the nth moment of x. Remember, the nth moment is simply the expected value of x raised to the power n, right? So this is the integral from 0 to infinity of okay, and this is, if you put the density that we got in part 2, right? Okay. Now we need to do this integration. I'm sure all you guys know integration better than I do. Now the way to do one way to do this is by substitution. So I'm going to make the following substitution. So set y equal to, which implies that x is equal to minus 1 over lambda times log of y, which implies that dx by dy is minus. Okay, let me put this in a box. Okay, now I'm going to make this substitute these into the integrand. So you get alpha lambda. Now the limits of integration: when x is 0, y is 1. Okay, and when x is infinity, y is 0. Okay, x to the power n will become this. E of minus lambda x is y, 1 minus y alpha minus 1. Dx will become minus 1 over lambda y dy. Okay, guys, so okay, a few things will cancel. The lambda here will cancel out with the lambda here, right? So what you get, and also I'm going to use the minus sign over here to change the limits from 1 to 0 to 0 to 1. So what you get is the following. You get alpha minus 1 power n divided by lambda power n, and inside the limits are going to go from 0 to 1 because I'm using this minus to reverse the limits, right? Then you have log of y raised to the power n, then 1 minus y raised to the power alpha minus 1 dy. You should also note that the y here cancels out with the y here. All right, so that's what you get. Now, in the next step, I'm going to use, I don't know whether you remember, there's a trick I mentioned earlier. Which, I did a video on something called the differentiation trick. I can write it down again. The differentiation trick, you should look at the video I did, says this, that anything of this form can be written as this is the differentiation trick, and I did a video. You should look at the course website. You'll see there's a video on this trick. All right. So what it says is that you can replace this by this. All right. So so you get alpha Okay. Right. Now I'm going to pull out the derivative sign outside of the integral. All right. So this will become integral from 0 to 1 of y power beta 1 minus y power alpha minus 1 dy set at beta equal to 0. Okay. Okay. Now you may remember also that that an integral of this kind is known as the beta function. I don't know whether you remember, I talked about this earlier. Let me remind you in case you forget. The beta function at values a and b is defined as the integral from 0 to 1 of t power a minus 1, 1 minus t power b minus 1 dt. All right, this is the definition of a beta function. All right, and using this, we can replace this integral by the following. So your a is going to be beta plus 1, and your b is going to be alpha. So this is the expression for the nth moment of x, x being the most expensive asset. Right? So this is part 3 of sheet 7. Now part 4, let me take this away. Part 4 of sheet 7 is asking you for the mean. Remember, the mean is simply the expected value of x, right? Right. So all you have to do is put n equal to 1 into the previous expression that we got. So if you do that, you get minus alpha by lambda derivative with respect to beta of the beta function at beta equal to 0, little beta, and not to be confused with capital B. Right. Now, one property of a beta function is follows. Now, if you have a beta function that can also be written as this. So this is a well-known property of a beta function. So using this property, we can write the above Okay. All right. Now you need to use the product rule to differentiate this, which I'm sure all of you know how to use the product rule for differentiation. So I'm going to just skip that part. And so after differentiating, if you set beta equal to 0, this is what you will get. You will get the following. All right, so this is the answer to part 4 of sheet 7. Now part 5 of sheet 7 is asking you for the variance, right? Let me start on a fresh page, sorry. So this is part 5. We want to find the variance of x, right, which I'm sure all of you know that it's the same as the expectation of x squared minus the square of the expectation, right? Now we already know what this is, right? So we just need to find the expectation of x squared. All right, so to find this, you just simply put n equal to 2 into part 3 of this question. All right, so if you put n equal to 2, you get, this is what you get. Okay. Now, once again, using the property that I mentioned in the previous step, right? All right. Right. Okay, this time you need to differentiate 2 times with respect to beta. So once again, you have to use the product rule 2 times. Now, if you do that, which I'm going to skip, if you do that, this is what you will get. This means that the second derivative of gamma function at 1 divided by alpha minus and plus all right, so this is the expectation of x power 2. All right, hence we have the variance. But this is the expectation of x power 2, and we already know the expectation of x from the previous part. Hence, we have an expression for the variance, right? Okay, so that completes part 5 of sheet 6. Now, part 6. Part 6 is to find the value at risk. Now, to remember, to find the value at risk, we need to set the CDF of x equal to p, and then solve for x in terms of p, right? So this implies, now, from the first part of the question, we know the CDF is equal to, this is the CDF of x equal to p, which implies that 1 minus right, which implies that right, and this implies that x equal to okay. So hence, the value at risk of x is equal to this is the value. So that completes part 6 of sheet 7, right? The next part is to find the expected shortfall. Remember the expected shortfall, you may recall, is defined by this. Okay. So if you sub this in place of this, you will get the following. Right. Now, this is not an easy integration to do, but what you can do is you can use the Taylor series expansion for log of 1 minus something. You may know from your calculus that the Taylor expansion for log of 1 minus, say, z is the following. Z to the power I divided by I. I think this should be 1, not 0, I think. This should be 1, excuse me for the mistake. So this is a well-known result you should have learned in your year 1 or year 2, right? Okay, so that the Taylor expansion for log of 1 minus z is minus of the sum from 1 to infinity of z to the power I divided by I. All right. So using this, excuse me again, I think this should be minus z to the power I. So using this, using the Taylor expansion, this is what you will get. You will get 1 over lambda p, the integral from 0 to p of sum I from 1 to infinity of t raised to the power I divided by alpha divided by I dt. Right? Now taking the integral inside the sum, so in other words, swapping them around, you will get 1 over lambda p sum I from 1 to infinity times the integral from 0 to p of ti divided by alpha dt. Now this integral is straightforward to work out. All right, so this will be 1 over lambda p the integral of this is going to be, I'll write it down straight away without having to work it out. Okay, I'm sure all of you know what it is. So it's going to be 1 over I p to the power I over alpha plus 1 and I over alpha plus 1. So this is the expression This is the expression for the expected shortfall, right, for x representing the most expensive asset, right? Right. The final part of sheet number 7 is estimation, is to find the maximum likelihood estimators for alpha and lambda. So basically, we are assuming that alpha and lambda are unknown, right? Okay. So suppose you have a random sample on x, right? Then the likelihood function, x being the most expensive asset, the likelihood function is a function of two parameters, alpha and lambda, right? It's going to be the product of the density function of x, which we already worked out in part 2. So if you look at part 2 of the questions, you will see the likelihood function, the density function is alpha lambda right. This is the density function of x, right? Now, if you simplify the product, this is what you will get. You get okay. All right. This is the simplified form of the likelihood function. The next step for MLE is the log likelihood function. The log so you take the log of this, so it's going to be okay, and plus okay. So that's the log of the likelihood function. And the next step is to find the partial derivatives with respect to alpha and lambda. All right, so right, with respect to alpha. Okay, let's do the differentiation with respect to alpha first. So if you differentiate with respect to alpha, you get n by alpha plus the sum 1 to n of log of, okay. And you should do the differentiation with respect to lambda. You will get the following: n by n by lambda minus the sum of xi and plus alpha minus 1 of the sum of the following. Okay. So basically you need to solve, so let's set this to 0 and let's set this to 0. So you will need to solve these two equations for the two parameters alpha and lambda. And it's not easy to solve them. I mean, it's not possible to solve them analytically. However, all right, let's call this equation 1. And let's call this equation 2, right? From equation 1, you see that you can write alpha hat, right, as the following: minus of n divided by the sum okay, and so it expresses alpha hat in terms of lambda hat, right? Okay, and so let's call this equation 3, right? Now if you substitute equation 3 into equation 2, you will get the following. You will get n divided by lambda hat minus the sum of, minus the sum of xi, n xi, then minus then multiplied by the following. Right, so you see that in this equation, the only parameter that appears is lambda hat. So if you call this, say, equation 4, you should call this equation 4, right? You can solve 4 because it involves only lambda hat, right? Equation 4 can be solved for lambda hat, right? Okay, and once you get lambda hat, right, you can use, once you get lambda hat as a solution of, or as the root of equation 4, use equation 3 to obtain alpha hat. All right. Okay, so that completes the last part